Well, hello everyone, and welcome to Prep 8. In this assignment, we're going to study the normal distribution and all the wonderful things about it. So we'd like to begin with an example. So here on the left, you have salary distribution data, and we have salaries for all 100 employees of a company. And those employees are labeled like E1, E2, etc. And then their name, and then their salary. And the salaries have actually been put in order, like that. Okay, so let's look at a few characteristics of this population. So the first thing we want to look at is what's the average salary? And the average is called mu, and this is what the Greek letter looks like for mu. It means average. And the way an average is calculated is you add up all the numbers, so all the x's, that's xi for each one, x1, x2, x3, etc., and then divide by the number of observations. But in Excel, it's even easier than that because we actually have a function called average. So we just type equals average and then highlight the range. And there's the average. Now, we'd like to get two other measures. Actually, the one we really want is down here. But on the way to it, we're going to calculate this one in the middle. And that's called the variance. And the variance is the average squared distance from mu. And the way that we would calculate that is we would take each of these salaries, subtract the average that we just found, square that, add all those squares up, and divide by n. But we can do that really quickly by typing equals BAR dot P, P for population, because this is population data. Again, the range. And that's our variance. So it's a pretty high number. For a lot of things, it's kind of a hard number to understand because it's squared differences. And that's why we go with the standard deviation, which is effectively the square root of that number, but it does have its own function. So it's standard deviation dot P, and then the same range. So it's 10,000. All right, so what does that 10,000 mean? It means that the mean of the population is around 50,000, and the standard deviation, or the average difference in salary, is 10,000. So let's use those two numbers, and then we're going to color code the distribution based on that. So let's start here with the mean. So that equals the mean up here. And then we're going to subtract one standard deviation. So that's going to be equal to this mean, and then minus the standard deviation. And then we're going to subtract one more. So we'll build off of this guy. So we'll take that minus another standard deviation. And then on the positive side, we'll again take the mean and then add, so plus one standard deviation. Looks like that. And then for our last one, take that number and add one more standard deviation. All right, so if I zoom out a bit, you can see what's going on here. And you'll notice that the number of employees that fall into each group changes. When we're close to the mean, a lot of employees fall within one standard deviation of the mean. So we can show it this way, or what you usually more traditionally see is something that looks like a histogram. So a lot of employees either side of the mean, close to, within 1 standard deviation, and then as you go between 1 and 2 standard deviations, a lot less, and then less than 2 standard deviations, less still. And this is the way that most things in the world are distributed. It's called normally distributed. And if you look at it, let me zoom in a little bit more. Typically we don't show it like this, but rather we take the gaps, we make them smaller, smaller, smaller. And so if you think of these bars as these little lines here, then eventually if we get enough observations, we get really a smooth curve, and that curve is called the normal distribution. And the reason that's a big deal is because we know a lot about the normal distribution. It has some statistical properties which we use to our advantage. So let's look at the normal distribution. The mean, again, is 49,953. That came out of the problem. Standard deviation is 10,081. And so I'm simply repeating these exact same gaps that we had here. So if I add 10,000, get to about 60,000, add another 10,000, get to 70, add another 10,000, get to 80, subtract 10,000, I'm sort of down at 40, subtract another 10,000, 30, another 10,000, 20. And these numbers don't come out exactly, but you get the idea. All right, now, the reason that is a big deal is because of something called the empirical rule, which goes right along with the normal distribution. And what the empirical rule tells us is that we know the percentage of observations that will fall in each of these gaps between, for example, 1 standard deviation out either side of the mean is going to be 34% of the observations. From 1 to 2 standard deviations is going to be 13.5, and you can see it's symmetrical on both sides. And then between 2 and 3 is another 2%, and then after 3 is the last 0.5%. And so sometimes this empirical rule is also called the 68, 95, 99 rule. Because if you think about it, within 1 standard deviation either side, 34 plus 34 is 68. Within 2 standard deviations, it's the 68 plus 13 and 5. 13 and 5 is another 27, so there's your 95. And then add another 2 and 2 is 4, and there's your 99. So we can use this to actually answer questions about the distribution, even if we don't have the original data. If the only thing we have are these two numbers, the mean and the standard deviation, we know a lot about the distribution and can answer these questions. So let's go ahead and do it. So what percentage of employees are in between 39,871, that's 1 standard deviation, and 60,034. That's 1 standard deviation this side. So it's between these 2 standard deviations. That's 34 plus 34%, 68. What percentage earn between 29, so around 30,000 and 70,000? So there it is. There's the 30,000, that's 2 standard deviations. There's the 70, another 2. So it's going to be that 68 plus the 13.5 and 13.5, it's going to be 95. And then between around 20,000 here and 80,000 here, so that's another 2 plus 2 is 4%, so we get to 99. And that's why it's called the 68, 95, 99 rule, the empirical rule, because depending on how many standard deviations you are away from the mean. All right. What salary is the mean, median, and mode? This is getting at the definition of a normal distribution. And in a normal distribution, the mean, median, and mode are all the same. So we know the mean, which is 49, or mu, it's 49,953. What's the likelihood that a randomly selected employee will earn 49,953 or more? Well, so that's half the distribution. Distribution's symmetrical. The whole distribution is 100%, so it's going to be 50%. What salary number is at the 16th percentile? All right, so how do we get to the 16th percentile? So I can bring this up. I can bring up the cumulative percentage by putting a little x here. And what this shows is that as we add these up, 0.5 plus 2 is 2.5, plus 13.5 is 16, plus 34, etc. So these are the percentiles here. So at the 16th percentile, that's basically equivalent to -1 standard deviation below the mean, and that's the 39,871. Oops. What percentage of employees earn between 70 and 80? So 70 to 80, that's 2%. Between like 40 and 50, 40 and 50, 34%. And what salary is at the 99.5 percentile? So there's 99.5, it's the 80,000. All right, and we got all our points. We're done. Just as a review, basically a normal distribution is just a histogram where there's lots of bars in it, and we're just making it real smooth, and we've got lots of observations. The little dots inside the histogram are effectively the number of observations in each of the bars. Sorry, in the in this normal distribution. Okay, so let's get a little more practice now with the empirical rule. So we'll go to the next one here. A major cell phone provider has determined that its average salesperson sells 100 smartphones per quarter, standard deviation of 15. Sales are normally distributed. So our population is the cell provider. The individual is the salesperson. The mean, we're not going to worry about this just yet. The mean is 100, so that's the average. It's going to be right there. Standard deviation is 15. All right, so let's get a few more numbers on here that'll help us out. So let's put a little x here to get the empirical rule. Those are those percentages that we need. And let's also put another x so that we get the cumulative frequencies. That would give us the percentiles. And then finally, let's put an x here so we see the mean actually show up. And let's put an x here so we see the standard deviation show up, as well as the rest of the raw data axis. All right, so now it kind of makes sense, right? We've got the mean of 100, standard deviation of 15. So if you go 100 minus 15 is 85, minus 15 is 70, minus 15 is 55, and on this end, 100 plus 15 is 115, plus 15 is 130, plus 15, 145. And now using this, we should be able to answer all these questions. So what percentage of employees sell between 85 and 115? There's 85, there's 115. It's one standard deviation either side of the mean, which is 34 plus 34 is 68%. What percentage sell between 70 and 130? There's 70, there's 130, two standard deviations either side of the mean. So that's going to be the 68 that we just got, plus another 27, 95. And between 55 and 145, so it's going to be that 95 plus the 2 and 2 is 4, so that's 99. So remember, there is, again, that 68, 95, 99 rule, which is the empirical rule. What sales number is the mode? Remember, the mean, median, and mode are the same in a standard deviation. So if the mean is 100, the mode has to be also. Which kind of makes sense, right? It's the mode means the where you're going to have the most values at that, the most entries or the most dots at that number. What's the likelihood a randomly selected employee will sell 70 or more? So here's 70. So 70 or more is everything this way. Now, unfortunately, our cumulative distribution has shown the other way. So that makes it tough because it's looking left. We might actually be able to change that and type right. And we can. I'll put it back to left in a second. But you can see 70 or more is going to be 97.5. Now, even if I left it at left, I could still get the 70 or more because there's 2.5% this way. 70 or more is everything this way, so the whole thing adds up to 100, so 100 minus the 2.5 is going to be 97.5. What sales number is at the 50th percentile? That's going to be 100. What percentage of employees sell between 70 and 85? That's right here. So that's between -1, -2 is 13.5. And sell between 100 and 130. There's 100, here's 130, so it's going to be the 34 plus 13.5, 47.5. And what sales number is at the 16th percentile? So there's the 16th percentile, it's 85. Pow! Okay, we nailed it. Let's go on to the next one. All right, now, with the empirical rule, we're always trying to get kind of approximate stuff. And now the question is, what if we want exact, like an exact number? In other words, we want a number that's between these lines, not right on a line, not right on a standard deviation break. Then we actually have to use some calculation. So let's look at this. Lucy sells in the East Division, where the average sale is 30,000. All right, so the population she's in is the East Division, and she's Lucy. All right, the average sale is 30,000. And the average distance from the mean is 4,000, so that's the standard deviation. And her sales are 38,000. Right, so she's out here. And what's her percentile? Okay, so in this case, we're looking, percentile means looking left, because we want everything this way. Now, actually, that's going to start way down here. But to get that last bit, we need to know the z-score. And to calculate a z-score, we're going to use these equations. So we're going from this, we're on this side, x to p of x, because x is her salary. P of x is the probability of her salary. So we need a z-score, which is going to be equal to x minus the mean, so it's the difference from the mean divided by the standard deviation. So it's basically the distance from the mean measured in standard deviations. That's why we divide by the standard deviation. All right, and now we can see there's Lucy in the East Division. We're looking left. Her x value is 38,000. Her z-score is 2. And now, what's the probability? So now we're going to use one of these two equations. Since we're looking left, we use the first one, which is going to be norm.s.dist. Norm for normal distribution, S for standard normal distribution, right, where the mean is 0 and the standard deviation is 1. So basically, we're calculating it for the blue values up here. That's why we needed to get the z-score, because the z-score is one of those blue values. Dot dist, and then the z-score. And then we pick true because we want the cumulative distribution, because we want everything leading up to that point. Excellent. Okay. And now we're going to do some answers just using the empirical rule. In other words, no precise calculation. What sales does Lucy need to achieve the 84th percentile? So in other words, if she's really high, but if she only wanted the 84th percentile, that would be a 1 standard deviation, which is here, 34,000. And what sales does Lucy need to achieve the 99.5 percentile? That's way out here. That would be 42,000. And biff. Okay, we nailed that one. Let's move on. Now in this problem, we're going to look for sales above. Okay, so we're going to be looking right rather than left. So Xavier sells in the Atlanta division, so the population is Atlanta. Did I spell it right? Maybe it's Atlanta division. Oh, okay, I must just have spelled that wrong. Atlanta. Xavier. Did I spell that wrong too? Xavier. There we go. It says what percent of sales are above him. So this one's looking right for the case. The mean is 35,000 for the division. The standard deviation for the division is 10,000. It's the average distance. And Xavier's at 50,000. All right, so he's here. And now we need his z-score. So that's x minus the mean divided by the standard deviation. All right, so now we finally need the percentage. And this one we would have to calculate because it's kind of hard to estimate it between here and here, especially since this line is sloping. So this piece of it has more probability than this piece, so we can't just take the halfway point. So what are we going to do? So we look back over here at our equations, and so we're at the looking right. The arrow is going right. So instead of just norm.dist, we use 1 minus, basically, because 1 means 100%. So we subtract the other half, or the other piece, and we get what's left. So as we pretend we're looking left, subtract all of that, and we get the little bit to the right. So that equals 1 minus norm.s.dist z true. So 6.7%. All right, now we'll go back to the empirical rule. So that was our precise one, but now let's just try to get more of a feel for the numbers, which is what the empirical rule allows us to do. What sales does Xavier need to achieve the top 2.5 percentile? So 2.5 and above comes at 2 standard deviations or more above the mean, which is 55,000. And what sales does he need to achieve the top 0.5 percentile? So that's this little bit over here. So this or more is going to be at 65,000. So he'd really be a rock star. And we're good.